We will start with some applications of Fubini's theorem. It will also give you some examples of functions which are in L1, so that you get familiarized with these spaces. We saw some of this earlier. We will see how Fubini's theorem and the polar coordinates help in deciding certain functions are in L1, and then we will see the convolution on L1. That also will be an application of Fubini's theorem. So, let us start with recalling the polar coordinates. Okay. So recall polar coordinates on Rn. Okay. So strictly speaking, it is Rn minus a point 0. We identify this with 0 infinity cross Sn minus 1, and we had two spaces, right, the Lebesgue sigma algebra of 0 infinity and r to the n minus 1 dr. So, that was our measure. So, one such. The other space was Sn minus 1, and we had a sigma algebra G and a measure sigma, right. So, what is sigma? Sigma was the measure defined by, if I take a set E, this was n times the Lebesgue measure of E tilde, where E tilde was the sector. So, E tilde is the sector defined by E, right. So, let me recall that this is simply all those points S times omega, where S was between 0 and 1 and omega was in E, right. E, remember, is a subset of Sn minus 1. So, some points on the unit sphere, you sort of draw the lines from those points to the origin, right. Do not include the origin. So, that is your sector, and you look at Lebesgue measure of that. So, that is your sigma. So, this gives us the polar coordinates. So, if f is suitable function, we have integral over Rn f dm equal to integral over 0 infinity integral over Sn minus 1 f of r omega d sigma omega. So, that is the inner integral r to the n minus 1 dr. Of course, if f is positive, you can interchange the integrals, or if f is in L1, you can interchange the integral, etc. Okay, so such things will be used in computations. But let us look at let us use those in some examples. So, consider the function. So, this is defined on Rn. Let us say it takes values in the real line. It is actually positive. So, f of x is going to be defined by 1 by 1 plus mod x to the n plus 1. Okay, so, n is the dimension. So, mod x is the usual norm of x, right. Mod x is modulus of x1, x2, etc. xn. This is summation xj square j equal to 1 to n to the half, right. Usual definitions. I want to say, so we want to prove or check. We want to check if f is in L1. Of course, this is a continuous function, so it's measurable, right. So, this is continuous, so measurable. Okay. So, such things do not cause any problem. Measurability. Question is, it's integrable or not. So, I want to compute the integral of f and see if it is finite. Okay. So, we look at integral over Rn. One should take mod f, but f is positive. So, f dm, right. This is what we want to compute, which is of course by polar coordinates. It is 0 to infinity integral over Sn minus 1 f of r omega d sigma omega times r to the n minus 1 dr. Okay. But f of r omega, so what is f of r omega? So, omega is a point in Sn minus 1, r is a positive number. So this is, well, the definition of f tells me that this is 1 plus mod r omega to the n plus 1. Okay. But mod omega is equal to 1, right, because omega is in the unit sphere. Okay. So this is simply 1 by 1 plus r is positive, so modulus of r is just that n plus 1. Okay. So this is independent of omega, independent of omega. Such functions are called radial functions. Okay. So this is same as saying f is a radial function. Radial means it depends only on the distance from origin. So radial function. So such functions do not depend on omega, they depend only on mod x, that is r. So this I can write as, so here there is no dependence on omega. So I have simply integral over Sn minus 1 d sigma, right. So that is some constant, okay, times integral 0 to infinity 1 by 1 plus r to the n plus 1 times r to the n minus 1 dr. So the constant comes out, okay. So this is a finite constant, finite constant. Well, why is that? So because this is the space measure of the whole space, right. What is Sn minus 1 by definition? So this is n times the sector defined by Sn minus 1. So you look at Sn minus 1, look at its sector. So what is the sector defined by Sn minus 1? That will be the whole unit ball. So n times unit ball. But unit ball has measure finite, right? It's a compact set. So it's a bounded set, so it has finite measure. So this is strictly finite. You can actually compute it. I'll tell you how to do that. So right now we need only that it is a finite constant. Now so we need to look at only this quantity. Okay. So let us look at that separately. Integral 0 to infinity 1 by 1 plus r to the n plus 1 r to the n minus 1 dr. Well, the integrand in r is a continuous function. So this is a continuous function in r. So it will be finite over any compact set, correct. So we need to look at only what happens at the infinity. So this I can write as integral, let us say 0 to 1 plus 1 to infinity. These are all Lebesgue integrals, by the way. We are decomposing the domain of integration into two sets, right. So that is all we have done. This part is finite because I am integrating a continuous function over a compact set. I need to look at only this part, right. So this is less than or equal to, well, I will write it as 1 to infinity 1 by 1 plus r. So 1 by 1 plus r is of course less than or equal to 1 by r, and I have n plus 1, right. So I have 1 by r to the n plus 1 and I have r to the n minus 1 dr. Okay. All right. So that directly tells us that this is equal to integral 1 to infinity r to the n plus 1 to the, so we have r to the n minus 1. So this is simply 1 by r square dr, and that is finite, right. So you can integrate this to be minus 1 by r from 1 to infinity, and this will give us some quantity, finite quantity. Well, you may want to justify this. So this is something which we have done before. You can always write this as limit k going to infinity integral 1 to k 1 by r square dr, because this is a positive function. So by monotone convergence theorem, this is exactly equal to integral 1 to infinity 1 by r square dr, right, by MCT. And here you can apply Riemann integration, right. So apply Riemann integration because we are on a interval, this is a continuous function, etc. Riemann integration, and you can compute the limit, right. So instead of doing this, you can do this in 1 to the k and take limit. Okay, so that is the standard method. So you have seen this before, so apply the same thing, so you will get that this is finite. Okay, so what we have proved is the function is in L1, right. So let me give you an exercise here. You can do the same thing with functions which are very similar. So 1 plus mod x. So instead of n plus 1, take n plus alpha, prove that this is in L1 or n for alpha positive. Okay, so that is what you should understand. So at infinity it should decay like n plus alpha for alpha positive. So faster than 1 by mod x to the n, it should decay like that. Then only you will have, so instead of r square here you will have r to 1 by r to the 1 plus alpha, and still the same thing will work. You can also check that e to the minus mod x square is in L1. This is much easier because exponential decay is very fast. So this follows immediately because e to the minus mod x square is less than or equal to some constant times 1 by 1 plus mod x2. Any power you want, in particular you can put n plus 1 or any other bigger power or any other bigger power. Okay, so you will get L1 immediately. Well, this allows us to compute something. So let me try to explain that. I'll leave the computation to you. So this is a positive function, right? It's a positive function and it's in L1. So integral Rn e to the minus mod x square dm. Okay, so dmx. Well, this I can write as, so I'll write it as integral over Rn e to the minus mod x square is e to the minus x1 square into e to the minus x2 square into etc. e to the minus xn square, right? Because mod x square is the sum of xj square. But now Rn, remember these are Borel measurable functions. So I can write Rn, if I write Rn as r cross r cross r, so this is a product space. So you have a product measure and these are Borel measurable functions. So I can replace this with d of m1 cross m1 n times, right, where m1 is the Lebesgue measure in R, right, or on R, on the real line. So you take the n-fold product of that is your Lebesgue measure on Rn. So we have seen that, right, Rm cross Rn has Lebesgue measure, n plus n dimensional Lebesgue measure, right, restricted to Borel sigma algebra, there is no problem, otherwise you complete it appropriately. So let us use this to compute this. So on the left hand side we can apply polar coordinates, okay, to get, well, what is left hand side? Integral 0 to infinity e to the minus r square. Remember it's a function of mod x, so there is no omega dependence, r to the n minus 1 dr, right, times sigma of Sn minus 1. So that is the total measure of Sn minus 1. Well, on the right hand side, so let's put this here, RHS apply Fubini's theorem, because we have a positive function. So order of integration does not matter, right, Fubini's theorem. So then this becomes integral over r e to the minus x1 square dx1, right, dx1 meaning dm1 x1, okay, I will simply write dx1, usual Riemann integral notation, integral over r e to the minus x2 square dx2, right, etc., etc., because these are independent of each other, so they all come out as constants, right. You can integrate in any order, so that is what Fubini's theorem tells you. So this gives me e to the minus xn square dxn, okay, but these integrals are all same, right, x1 x2 x3 x are all dummy variables. So this is simply integral over r, so I will simply use y e to the minus y square dy, and then I have n of them, so to the n, okay. So you can compute both sides, so you can compute this and this, okay. So compute these two, so you can do that by these two integrals. You will get expressions in gamma and so on, gamma and n factorial and things like that, and then you will get an expression for this, okay. So I will leave it to you and consequently find the total measure of sun minus. You can check that it agrees with whatever you know in R2. For example, if I look at R2, I have the circle and the measure of the circle, right, in with respect to sigma. So this will be S1. Sigma of S1 by definition is 2 times, right, n times the Lebesgue measure of the sector. Sector is the whole unit sphere, right, unit ball. So units, unit circle or unit ball in R2. Unit ball in R2 has radius 1. So you know what the area is, right. So area is pi r square, r is 1, so it's just pi. So this will be 2 pi. 2 pi is the circumference of the circle, right, of radius 1. So that's precisely what the measure is. So you can compute this and check that it's true. Okay, so that will give an expression for sigma s n minus 1 in general. Okay, so it's another application. Okay, so one more exercise. Okay, consider the function f of x equal to mod x to the minus alpha. Now alpha is positive times mod x less than or equal to 1. So I am looking at the characteristic function of mod x less than or equal to 1 and multiplying by mod x to the minus alpha, alpha positive. Okay, let's see when is it in L1. Okay, so if I want to integrate this, so I'm going to integrate Rn mod x to the minus alpha indicator of mod x less than or equal to 1, right, dx. So dx here, this is the Lebesgue measure. Lebesgue measure. Okay, but so because of the indicator function, the integral is not on over Rn, it will be on this set, right. So this is simply integral mod x less than or equal to 1 mod x to the minus alpha. I can also do that dx. Apply polar coordinates because I have a function of mod x, again there is no dependence on omega. So I will get that sigma n minus 1 outside as earlier. Now I am on mod x less than or equal to 1. So if it is on Rn, I go from 0 to infinity. Because of this I will go only from 0 to 1, right, r to the minus alpha times r to the n minus 1 dr. Remember that extra measure there. So this is equal to sigma s n minus 1, which is a constant again, integral 0 to 1 r to the so let me write this as n minus alpha times r to the minus 1 dr. Okay, now check that. So you can again so recall how we did, recall calculating integral of 0 to 1 by root x dx, right. It's an unbounded function. So similarly, depending on what alpha is, this can be unbounded, but then you can always cut it at 1 by k, right, and look at 1 by k to 1, apply monotone convergence theorem to compute this. So you do that. So check that f is in L1 of Rn if and only if alpha is less than n. Okay, so I should have something positive here. Remember here there is a minus 1. R to the minus 1 is not integrable. 1 by r dr will give me log r, and then there is a problem at 0. But the moment I have something some positive power here, it would be integrable. Okay, so that's the point. So that's a simple computation, but that you can use polar coordinates, Fubini's theorem, etc. to do. Okay, so another application, so that's called convolution on Rn. So we'll use Fubini's theorem again. So let's take f and g in L1 of Rn. Okay, convolution of f and g is defined to be, it's another function, so we'll denote it by f star g. Okay, so f star g at x equal to integral over Rn f of x minus y gy dy. Okay, we'll of course justify it. So of course this is also equal to integral over Rn f of y g of x minus y dy. Okay, so that follows from use translation invariant of invariance of Lebesgue measure. Okay, so that's the usual change of variable you will do in Riemann integration. You put x minus y is equal to t, then dx dy equal to dt, etc. So that kind of change of variable, but that is essentially translation invariance of Lebesgue measure. Okay, so the claim is that, of course we don't know whether it exists or not, right? I have L1 function, so if I multiply two L1 functions, I need not be in L1. Okay, so that is something you should always keep in mind. For example, you look at 1 by root x inside 0 1. Okay, so times 0 1. This is in L1, I know. Okay, and again you take 1 by root x is also in L1. If I multiply, I'll get 1 by root x into 1 by root x is 1 by x, right? But 1 by x is not integrable near 0, so it's not in L1. So I don't know what happens to this integral. Okay, just because there is a translation, you will see that it exists almost everywhere. So let us see that. So what you do is you start with, so claim is that if f g are in L1 of Rn, then f convolved with g is also in L1 of Rn. Okay, so this is rather interesting, because the product of L1 functions need not be in L1, but the moment you translate and then take the product and integrate, you are going to get something in L1, which means that the integral of this, so it is in L1, so it has to be finite almost everywhere. So this integral exists for almost all x. Okay, we will see why. And so it's not just that the convolution is in L1, the L1 norm of f convolved with g is less than or equal to L1 norm of f times L1 norm of g. Okay, so there is a bound as well. So let's see, the proof of this is sort of straightforward. Okay, so we have the convolution definition here, so we use that. Okay, so problem here is f and g are not positive and so on, so we will simply work with mod f and mod g. So you look at mod f of x minus, well, first of all measurability. So I should tell you why. So f and g are in L1, so they are Lebesgue measurable, right? And I am taking the product, so I need to show that that is measurable and then take the integral, right? So there is x, y and so on. So what you do is you look at the map x comma y going to x minus y, so let's call that phi. So phi is continuous, right? Well, where is the map going from? So this is Rn cross Rn, which is R to n, going to Rn. This is a continuous map, and then you compose with f, which is a measurable function. Okay, so to get f of x minus y. Of course, we don't know if this is measurable. This map may not be measurable. We don't know that because f is only Lebesgue measurable. But recall the theorem we proved yesterday in the last lecture, that if f is measurable, there exists f naught Borel measurable such that f equal to f naught almost everywhere, right, with respect to the Lebesgue measure. So I can replace f and g with Borel measurable functions. Okay, so without loss of generality, so I should do that first. Without loss of generality, assume that f and g are Borel measurable. Okay, Borel measurable. We can do that because if f and g are Lebesgue measurable, there are Borel measurable functions which are equal to them almost everywhere, and the integrals don't change. So this expression will not change except on a set of measure 0, which we can discard. Okay, all right. So now if I go back to this maps. So I have x comma y going to x minus y, which is a continuous map, right? This is a continuous map, and f, which takes to f of x minus y. So this is a Borel map, okay, Borel measurable. Okay, so I'm going from Rn cross Rn to Rn to R, right? R or C or whatever, does not really matter. And I want to know if this map is measurable. Okay, so what exactly is this map? This is f composed with phi, okay, from R2n to the real line or complex plane, depending on what f is. Well, this is measurable because E is measurable. Why is that? Well, if V is an open set contained in the real line or complex plane, open, then I need to look at the inverse image of V, right, and see where I land. So f composed with phi inverse of V, right? I want to know whether this is a Lebesgue set or not, right? So this is equal to, well, this is phi inverse of f inverse of V. Okay. Well, what can I say about f inverse of V? F is a Borel function, right? So it's a function from, it's a Borel measurable function. So it's a function from Rn to Rn. So f inverse V, if I pull back a open set by a Borel measurable function, I will land in the Borel sigma algebra of Rn, right? Now phi is continuous, and so it will pull back Borel sets to Borel sets. Okay, so phi inverse of f inverse V, because this is a Borel set, will be in the Borel sigma algebra of R2n, right? Because phi is from R2n to R. So this is in the Borel sigma algebra of R2n, and so this function is f of x minus xy going to f of x minus y is a Borel function, Borel measurable function. Similarly for g, okay, gy. So you can integrate them. Okay, so integrals make sense. It may not exist, we don't know that. So now consider the integral of Rn modulus of f of x minus y modulus of gy dy. Well, what is the advantage in taking modulus? Because it's a positive function and the integral will exist. It may be infinity, but it will exist. Modulus does not do anything to the measurability, right? Now if you look at this function, okay, if you look at this function, this is a function of x, right? This is well defined. I want to know whether this is finite or not. For that I look at one more integral over Rn and this function. So that is integral over Rn modulus of f of x minus y gy modulus dy and dx. So all these are Lebesgue measures, by the way. So I am not writing m, we simply write, because there are different variables, dmx and dmy would have been okay, but dx dy will denote Lebesgue measure on the corresponding spaces. But now I have two integrals, but these are positive functions, right? Positive functions. So apply Fubini's theorem. These are all sigma finite measure spaces. I have positive functions, so I can apply Fubini's theorem. So we will get integral. So it doesn't matter what order I integrate, right? So instead of integrating with respect to y first, I will integrate with respect to x. This g has nothing to do with x, so that comes out. So I will have modulus of gy, and then I will have integral over Rn mod of f of x minus y dx, right, dy. So that is just Fubini's theorem. But what is this? The Lebesgue measure is translation invariant. So if I translate the function and integrate, I will get the integral of the function. Okay, so this is equal to integral over Rn mod f of x dx, right. So, in Riemann integration you will put x minus y equal to something and etc., etc. So, same thing, which is translation invariant of invariance of Lebesgue. But now this is a constant which has nothing to do with y, and I have L1 norm of g. So, this becomes L1 norm of f times L1 norm of g, correct, which is finite because f and g are in L1. So, if I look at this function, this is in L1, and so it is finite almost everywhere, and is finite almost everywhere. Okay. So, we so just one more step. So, this simple, so you can conclude that f convolved with g is actually in L1, and L1 norm of f convolved with g now is less than or equal to, because you are taking the modulus inside, you will get this quantity, which is L1 norm of f into L1 norm of g. Okay, so we will stop here. So, we just saw some simple applications of Fubini's theorem and polar coordinates. So, we will continue a little bit more using Fubini's theorem, and then we will go to a new topic called complex measures. Okay.